Hello and welcome back. In this next section, we're going to be looking at expected value or expectation. Expected value is used in a bunch of different scenarios. Lotteries and casinos use expected value to find out what they should charge people in terms of offsetting what the payouts should be. Insurance companies use expected value because they're betting that you won't have an accident, which means they get to keep their premiums, and you're thinking that if you do have an accident, you get a payout from them. And those two things need to offset themselves in order for the insurance company to be able to stay in business. If a construction company wants to figure out how long it could expect for them to complete a job, or for a business, they want to find out in the long run what they could expect to make on a business venture, whether or not it's going to end up in a profit or a loss for them, expected value occurs in a lot of different scenarios. So for expected value, what we look at when we're going to be computing it is expected value, which we typically use the letter E to indicate what that value should be. We're going to be looking at the probability a certain act or action occurs, okay, which is going to be denoted with these capital P's, and then the probability is going to have an associated either payout or loss to the person or the company, which is going to be symbolized with these A's. So then what we're going to be doing then is we would multiply the probability times the payout or loss, and we're going to be doing that over all of the different possibilities that would be in the sample space for the experiment. Alright, so this ends up being the formula for expected value, and we're going to be using this over a couple different scenarios so you can see how this is applied. So again, these P's right here, these are probabilities of the different scenarios happening, the likelihood of the different actions happening as a result of the experiment. And then these A's right here, this is going to be either the amount won or lost. Or you can think about it as being a profit or a loss, depending on the scenario that we're looking at. And we're just going to be doing that over all the different possibilities as a result of the experiment. Now we're going to keep in mind as we start going through the examples that we consider to be a game is considered to be what we call fair if the expected value of the game is 0. All right, so let's kind of see this in action in this first example. Alright, so a child asks his parents for some money, and the parents are going to make the following offers. The father says the child will flip a coin, and if the coin lands heads up, the father will give the child $20. If the coin lands tails up, the father will give the child nothing. The mother's offer is the child will roll a 6-sided die. The mother will give the child $3 for each dot on the upside of the die. Now the question is, which offer has the greater expected value, and is either game fair? So let's analyze either of these situations. So let's take a first look at the father's offer. Now for the father's offer, keep in mind that when a particular trial of the experiment runs, when the coin gets flipped, it will either be heads or tails. Depending on which one lands, either the father gives the child $20 or the child gets nothing. So on one trial of the experiment, that's what could happen. What expected value will figure out for us is if this child would repeatedly play this game over and over and over again and average all of those either earnings or losses, and the loss in this case would just be that he doesn't get any money. If you were to average those in the long run, what would that average be? That's what expected value is. So these are the two outcomes that could happen as a result of the experiment. For each one of these, we're going to analyze the probability it happens and then the payoff to the child. So if heads lands, the probability that that happens is 1/2. If a tails lands, the probability that happens is also 1/2. So that's for the probability. Now let's take a look at the earnings. If a heads lands, the earnings to the child would be $20. If a tails lands, the earnings to the child would be 0. Now we have everything we need in order to compute expected value for this scenario. So the expected value, for each of the different scenarios, we're going to take the probability it happens times the earnings, or the amount of money won or lost, and then we're just going to add that over all the different scenarios. So this would be how we would set it up for the heads case. So the probability it happens is 1/2, and then the earnings would be $20. For the tails case, the probability that happens is 1/2, and the earnings in that case would be 0. And if we go ahead and compute that, we'll get then the expected value in this case is going to be $10. Alright, so what we're finding here is that if the child would repeatedly play the game over and over again, and sometimes the child will get $20 and sometimes the child will get $0, if the child were to average those winnings in the long run, the child would average earning $10. Now let's take a look at the mother's offer. Alright, so the mother's game is going to be a little bit more complicated. So the child will roll a die. So the outcomes on a die would be 1, 2, 3, 4, 5, or 6. The probability of getting any one of these numbers is 1/6. So the probability of getting a 1, let's maybe keep track of what we're recording here. Those are the different outcomes. Now we're going to find the probability. So the probability of each one of these is going to be 1/6. And then let's go ahead and find the earnings to the child. Now the mother will give the child $3 for each dot on the upside. So if a 1 lands, that's only 1 dot, so the child will only earn $3. If a 2 lands on the die, $3 for each dot, then that means the child earns $6. If a 3 lands on the die, the child earns $9, then $12 for 4 dots, $15 for 5 dots, and $18 for 6 dots. So let's go ahead and figure out the expected value then for the mother's offer. Okay, so for each of the different scenarios, we're going to take the probability it happens times the amount of money won or lost. So this outcome, there's a 1/6 of it happening, and the child would earn $3. We're going to add that to 1/6 times the $6. So we're just taking each of the probabilities and multiplying it by the earnings, and we're going to do that for all of the different scenarios. So 1/6 times 12 plus 1/6 times 15 plus 1/6 times 18. Okay, so let's go ahead and clean this up a little bit. So this is going to be then multiplying these fractions together. We get 3/6, that'll be 6/6, 9/6, 12/6, and I'm just going to leave it like this because now I already have my common denominator, so when I go to put all these fractions together, it'll be nice and easy to do that. Okay, so for these different 6 scenarios, I get these values, putting all my numerators together. Let's see, that'll be 63 over 6. We go ahead and do that division to figure out what the expected value will be. That'll be 10.5. or $10.50. Alright, so what we just found in that case is in the long run, if the child would repeatedly play the mother's game over and over and over again, sometimes the child's going to win $9, sometimes the child's going to win $3, sometimes the child's going to win $15, and so on and so on. If the child were to average the earnings over multiple trials, and this is playing the game many, many times, if the child were to average those values, the average of all those numbers would be $10.50. So, which offer has the greater expected value? The mother's game has the greater expected value. Is either game fair? Well, a game is considered fair if the expected value is 0. So is either game fair? No. Neither game has an expected value equal to 0. So what we're actually finding here in this case is that the child will actually make money in the long run in both scenarios. The child has a better advantage of the mother's offer in the long run if they were to play the game over and over again rather than on the father's game. Now keep in mind, on one particular trial of the experiment, the father's offer, the child has half a chance of getting $20 and half a chance of getting nothing. Okay, so the child takes a gamble on the father's offer that then when they play the game, he might walk away with nothing, but he also might walk away with 20 bucks. On the mother's offer, every time the child plays, he's going to win something, right? He will never walk away with nothing. There's always a chance of winning. And on the mother's offer, the most money they could win is $18. Okay, so both offers have positives and negatives in a single trial of the experiment. What expected value tells us is if the child were to play the game over and over and over again, what would the average winnings be? So the child could expect in the long run to make out more money on the mother's offer than the father's offer.